So here's an implementation in Python of the Taylor series expansion. We will generate a sine wave of 500 Hz, and we will have 48 kilohertz as the sampling frequency. So we have here a function that will implement this formula here. So if we notice here, we have here a sine, we have the factorial, and we have a power term. So this is what we will do here. We are defining sine. This is the sum. So the sum is the sum of all the terms. Then we have a factorial that will calculate the factorial, and we have the power that will calculate the powers. So here we have a function that takes a value and takes a precision. So if we want to calculate the sine of 0, we put 0, and then here we decide how many terms we are going to use. So here if we're going to use 1, 2, 3, 4, 5, how many terms we need. So and here we will, inside this loop, the term is the sine times the power divided by the factorial. So it's the sine times the power divided by the factorial. This is a sum. So the sum gets updated. The sine gets toggled. Then we have here this factorial is getting calculated, and we have this power also being calculated. So now we will call this function. So it's the 2 pi 500. So this is the omega. This is our sampling frequency, and we are using 11 coefficients, and then this is our amplitude. So we are calling this, and we see that for the beginning it is a sine wave, but if we continue generating for bigger values, we have this huge drop. And actually, if we make it even higher, we see we have all these rounding errors, all these errors due to not using enough coefficients, because if we increase the number of coefficients, we get more similar, our approximation of the sine wave is better. So here we need to decide, the more coefficients we use, of course it's more computational demanding, and it takes more time to process, and maybe our processor will not be able to handle so many calculations in a short time for real time applications. But as I mentioned, we can take advantage of this symmetry and periodicity of the sine function. So if we'll just generate a quarter of a sine function, so this part here is the mirror version of this part here, and this part here is the negative of this. So with just 1/4 we can generate the full cycle and then repeat itself. So we will not implement this Taylor series in C, because the Texas Instruments C5515 processor has a built-in DSP library which has a sine wave function that is based on the Taylor series, and we will take a look at this function. It's highly optimized, so we can have in real time, and we don't need so many calculations like if we would do this way.